This section is about collisions. For an isolated system, we find that the total momentum of that system is always conserved. And this has some big implications when it comes to the principles of collisions. We have to add up the momentum of all the objects that are involved in the collision. And whatever that initial sum of momentum is, if the system is isolated, then the final sum of the momentum has to equal that initial sum. That's going to be true for any type of collision in the universe. Now let's look more specifically at elastic types of collisions. And there's a classic example of this. A cue ball strikes an 8-ball head on. If you've ever seen this before on a pool table, you fire the white ball directly at the 8-ball with a certain speed v. They come into contact. They exert forces on each other. There's a loud sound. And then the 8-ball travels away from the white ball with the same speed that the white ball had come in with, but the white ball stops completely. It's a classic example of a perfectly elastic collision. Now, in the real world, there would be some energy losses to the environment, so it wouldn't be ideally perfect in every sense, but it is very, very close. So when the white ball strikes the 8-ball, we can have heat flow, we can have sound given off. These are things that would take energy out of the system. But what do we need for an elastic collision? Well, we need for the sum of the initial momentum to equal the sum of the final momentum. And as you can probably see here in the diagram, the momentum that the white ball carries in before the collision is transferred to the 8-ball who leaves the scene after the collision takes place. So the momentum is conserved. You might also notice that the kinetic energy that the white ball carries in with it before collision would actually equal the kinetic energy that the 8-ball goes away with. That's just one example of a perfectly elastic collision. Let's take a look at an inelastic collision. For an inelastic collision, we find that momentum is still conserved. But the difference here is that kinetic energy is not conserved. The initial kinetic energy will be greater than the final kinetic energy of the objects involved. Imagine two clay balls traveling toward each other with the same speed. The clay balls stick together into one mass, and they end up at rest in the center. This is an example of what's called a perfectly inelastic collision. What happens is momentum is conserved. Because momentum is a vector, the direction matters. Let's call the mass on the left object 1, and the mass on the right can be object 2. The one on the left carries in a momentum of m times v. The one on the right carries in a momentum negative mv. If we want to find the initial momentum before the collision occurs, all we have to do is add their momentums. P1 plus P2. That is called the sum of the momentum. And as you can see, it's going to be mv minus mv, and that's 0. The initial momentum is 0. Now let's find the final momentum. The mass has a size of now 2m because they're equal sized objects. But its velocity is 0. And so the momentum at the end is also 0. This showed conservation of momentum. But was there conservation of kinetic energy? The answer is no. Kinetic energy is not a vector, so direction doesn't matter. All we would do is just add up the sum of the kinetic energies of the individual particles before they had collided, and then compare that to the kinetic energy of the mass after collision. But we can see clearly here that the kinetic energy at the end is 0. But the kinetic energy at the start is clearly not 0. Those objects do have kinetic energy. So what we see is that although momentum was conserved here, kinetic energy wasn't conserved. Not only was it not conserved, but the maximum possible amount of kinetic energy was lost in this collision, and that's what makes it a perfectly inelastic collision.